Alright guys, welcome back. My name's Alex, and today I'm here to talk to you about natural deduction, a system of proof that we were taught in class. So, two main questions we got to ask first. What is natural deduction and why do we use it? In very simple terms, natural deduction is a proof system. It's a way we can generate proofs of logical statements by constructing them in very different ways, right? Its main purpose is what's known as deduction, right? A deduction is where we prove a conclusion from a set of assumptions. These two words are important. And it is often used for formalizing and verifying mathematical and logical arguments. This system, natural deduction, is highly rigorous. There's no ambiguity whatsoever. So if you make a proof that works in natural deduction, it's going to be true. And it works with computers. That's a very important thing. You can chuck your proof into a computer and it can tell you this is right or this is wrong. What's very important about natural deduction is that there are no semantics involved. We don't care that certain statements have the same truth values as other statements. Right? Even though we're dealing with logic, we don't really want to think about, is this variable going to be true, this variable going to be false? We don't care about that. What we care about is how we rewrite statements. Seems kind of counterintuitive. But remember, there are certain logical leaps that you can't make. For example, De Morgan's in logic. If you know if you take the negation of P and Q, it's the same thing as saying not P or not Q, right? You can't make that jump in natural deduction. You have to get from one side to the other step by step. In logical equivalences, you can just jump that. Right? So that's a big difference. And interestingly, there are multiple systems of natural deduction. They're used differently all around the world, and I'll introduce the system that I'll use, along with the rule names that I'll use. These were the ones that I was taught. However, it can be said that all the systems are equivalent, and I'll leave that as a proof for the viewer. Now, let's get into how we use it. First off, let's talk about the overall concept, right? For human interpretation, at least, we have a high-value approach of what we do, right? First off, we make assumptions. We list them down as assumption 1, assumption 2, etc., 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 and these are the assumptions that were either given to us or that we introduce. And then we do something called formula rewrite, right? We will rewrite certain formulas based on the assumptions, based on the rules that we have or can introduce. And then, eventually, we will reach what is known as a conclusion. The conclusion is the thing that we want to reach at the end. Once we reach that, we've finished the proof. Now, let's talk about the rules. Natural deduction is a set of rules, and they have specific names, and you have to remember each one and how to use them. It's like a programming language. You have to remember how certain function signatures work, or how to set up a certain syntax, right? For example, in Python, right, you have max AB, right? And it tells you the maximum between A and B. You've got to remember that max, you have to either put in iterable or two variables, something like that, right? So you've got to remember each rule's function signature, how to reference. There are 11 rules down here, and these are as follows. Assumption introduction is where we introduce an assumption, right? If we have an assumption, we want to introduce it, we just cite that, and we can move on. Conjunction introduction is where we introduce a logical and. Conjunction elimination is where we eliminate a logical and. Similarly, disjunction elimination and introduction are where we remove and introduce logical ors. Implication introduction and elimination is where we introduce logical implications, right, or eliminate them. Falsum is known as a contradiction. It's an upside down T, right, and it means universally false. We've reached something that shouldn't happen. So sometimes we need to introduce these contradictions. That's where elimination and introduction come in. Finally, we have negation, introduction, and elimination. This is where we can either introduce a logical not or remove one, right? This video only serves to introduce the rules. In later videos, I'll go into detail of what each of these rules mean and what they can do. This way, viewers that are already familiar with it don't have to sit through me droning, right? Now, let's talk about syntax. A natural deduction proof question is typically presented like this, right? It'll say prove a set of assumptions and then this weird little sideways T, right? This is called the turnstile, and then we reach a conclusion. It's like sort of in maths, if you see an equation, you have to equate the left hand to the right hand. In this case, if you see this, you have to take all the assumptions on the left and make it turn into the right, right? When we write any kind of mathematical logic statements, we have to make sure that we follow the correct syntax. For natural deduction, there's many ways to set up a proof, and the way I was taught is the way I will teach you. And we use what's called a natural deduction table. There are many different ways to set them out, and if you look on the internet, they will seem very messy. This is the way that I think it's the clunkiest, definitely. It doesn't look very elegant, but you can clearly see what references were made, what assumptions are used, and that you start and end with the assumptions in your assumption set. Right? So here's what a proof would look like. If something this is prove the contrapositive, and it's a pretty simple logical equivalence. P implies Q, goes into not Q implies not P. Pretty elementary, right? We have a 5-column table. The first one is the line. It's like a programming language on an editor, right? You can cite the line that you're talking about. Assumptions are slightly different. Assumptions are the assumptions that we introduce or use in that line. For example, here. Although we're on line 6, what we're using is assumptions 1 and 5 in what's known as implication elimination, right, to derive a formula Q. The formula tells us what we're dealing with currently, and then justification tells us the rule that we're using. Finally, references allow us to reference the lines that we're talking about. For example, if you have P implies Q and P, you can get Q, right? That's what the references tell us, 5 and 1. And this is the conclusion that we get. Eventually, we'll reach what's our last line, right? And our last line should be what's on the right-hand side. And we should only end up with the assumptions that we started with. Now, this is where we get into assumptions, right? Assumptions are a key part of natural deduction. It took me a while to understand. Essentially, we have 2 types of assumptions. Those that were in the problem originally, and those that were artificially introduced and that we must discharge. Up here in this table, there's some prime examples. This assumption right here, P implies Q, was one that was originally in our question. That means we can keep it. However, here, and here, and here, right, those weren't in our original question. So we can't keep them. 3, 4, and 5 should not appear in this last line, right? And then you see we've actually eliminated them. Interestingly enough, right? There's several key methods that we can introduce and discharge assumptions with. For example, do you see on this line, right? Implication elimination. We've lost an assumption. We had, we actually introduced an assumption here, right? Because we combined 1 and 5, that means we have to have both. But here in negation introduction, we actually lost assumption 5. If you look at 5 and 7. I know it'll not make much sense right now, and I felt this way too, but I will go in depth later on. So, yeah, just to reiterate, right? It's important to recognize that at the very end, when we say that our proof is complete, we can only have the assumptions that were initially part of the question's premise. No more than that, but we can have less. If you somehow manage to prove not Q implies not P from nothing, good on you, right? But what you can have is you can only have those that were in our original premise or less, right? This is why assumption discharging is important. Now, here is a demonstration of proofs, right? Just to get you guys visually tuned. Here are 2 proofs for the same thing and really help me understand the difference between what natural deduction is and what, logical equivalences are. And they prove the same thing. This is known as the contrapositive. And one's done in ND and the other with logical equivalences. So the first one you just saw. We start with P implies Q. We introduce a weird negation, and then we work our way through cases, reaching contradictions, eventually negating our way out of this contradiction that we made, right? I'll leave this on the screen for a bit so you can take a look at it if you want. But down here is where we deal with logical equivalences. You can see it's much easier, but there's a slight difference, right? We have different laws. We introduce an assumption, right? And then we have conditional law, commutative, double negation, conditional. What we've done is we've turned this into the definition, rearranged it, added a double negative, and then put it back in, right? This one down here uses what we call semantics. We draw the rules based off the meaning themselves. This and this mean the same thing. This and this logically mean the same thing. Although you can't really get from this step, you still have to do step by step, but like this to here, right, is completely different in natural deduction. This step 4 to step 5, right? In natural deduction, we don't do anything to do with what meaning is, apart from, I guess, kind of looking at falsums, right? For example, if you look at line 7, I guess this is a prime example of why we have to work differently in natural deduction. what we've done is we introduced something called P, right? We get Q based on this first line's assumption. Because we introduced not Q, we get a contradiction. And then we choose to negate not P, and then we get down to here. Right? And the unique thing that I've been finding with natural deduction is that almost every proof is different. So you have to really learn to gather an intuition by, looking at a lot of different questions. And that is what I want to cover later on. Right? There's several very difficult concepts in natural deduction, such as introducing assumptions from thin air. It's possible to prove what's known as a verum, something that's always true. For example, A or not A, that's always going to be true. You can prove it from nothing. How do you do that? That's what I'll go over later on. Right? We can also introduce new variables seemingly out of thin air. Because of the ways disjunctions or implications work, we can sometimes just pull variables out of thin air and we don't even care about that they weren't in our original assumption set. The usage of proof by contradiction and negation, those are also very important. Up here was a proof by contradiction. Contradicted ourselves, and then we had to remove that negation, right? And there's so many more different concepts, so stick around. Thanks for watching.